Good morning. Well, I'm Dr. Craig Stark, and I'm going to be talking to you today about how the brain changes with age, but also some of the things that we may be able to actually do for it, how we may even be able to use things like 3D video games as a way of actually improving your memory. All right, so the take-home messages for today, what I'm going to try to convince you of, is that we have a structure in the brain called the hippocampus, and that this hippocampal memory system, it changes with age. And that leads to changes in our memory with age. So we lose some of the details of our memory as we age. But we can use something called environmental enrichment as a way of actually being able to improve your memory, improve hippocampal function. And we can do this even by using, well, commercial video games, believe it or not. So that's what we're going to try to convince you of today. So first off, a little bit of an overview. What gets worse with age? Okay, fine. A number of things do get worse with age. A number of things do get better with age. But in terms of our memory, we lose the details of our memory. We lose the specifics. So we may say something like, I know I remember it, but when was it? Or I know I've seen her and I know I've met her, but who is she? And I know I came home and I put my keys down, but where did I put them? All right, now these kinds of things actually happen to you all throughout life, but they do get worse as we age. So extensive research in my lab and in other labs have shown that this happens because of changes to your hippocampus. All right, so what's the hippocampus? Well, let's meet the hippocampus. You may notice this side profile here. This is my head, so I can do the gratuitous 3D animation, spin it around. This is an MRI scan. I can slice into the middle of my head here, come back out a little bit, and I can highlight this structure right here. That's the hippocampus. Buried deep inside your brain. You have two of them, one on the left and one on the right. And if I were to take this out, you would say, oh my gosh, look at that. That looks like a seahorse. Okay, hippocampus is the Latin word for seahorse, and I suppose if you're an anatomist and you're just staring at brains all day, you've got to get creative somehow. In any case, that's the hippocampus. Okay, so we know a lot about how the hippocampus works, and we know a lot about what it does. It uses a computation we call pattern separation, and the whole idea is it tries to get it so that very similar experiences can get represented in your brain in distinct ways, so it can keep these things from interfering with each other. So you can have clean, detailed, accurate memories of specific episodes. So you can recollect and go back to some point in time and remember the events that happened that time versus a similar day. You can remember where you learned something, the source of a memory. All of this we know is what the hippocampus is actually doing for you. All right, so if we know that, we can then design a memory task that is really keyed to index how well the hippocampus is working. There have been a lot of memory tasks out there for years, but back in 2006 or so, a graduate student of mine at the time, Brock Kerman, and I decided to devise a new memory task based on how we know the hippocampus works. And I can tell you how the task works, and yet it's still going to end up giving you the, you can still participate in my studies here. I show you a series of objects here. Maybe I ask you, is it an indoor, outdoor object? And I really just want you to try to encode, but try to get that into your memory here. At test, I can give you a test in which you may see exact repetitions like that clover. You may see things that you haven't seen before, like the rubber ducky. Or you may see ones that are very similar but not exactly the same thing, like this picnic basket. It's got blue instead of red. Or this seahorse. You can see these are two slightly different seahorses. All right. Now it's the memory for those details, not just, yeah, you showed me a seahorse, but you showed me that seahorse. That's the key in all of this task here. And we know, for example, if you take people who have damage limited to their hippocampus through some accident or through some disease here, they can do just fine when you're doing something like, well, okay, yeah, you showed me the four-leaf clover and you didn't show me the rubber ducky, but they do really, really poorly when we ask them which one of those seahorses did you see. So those are the red bars, those patients versus the healthy controls, folks like you. So for a while, this was called the rubber ducky task because I always used that, and that's why there's a rubber ducky back there. It got the name the mnemonic similarity task because to be a part of huge multi-million-dollar or $300 million clinical trials, you need a cooler name than the rubber ducky task. But so it's the mnemonic similarity task, testing these highly similar objects. And we know it's a great index of hippocampal function. This gets worse as we age. So what I'm showing you here is people in their 20s and 30s, 40s and 50s, 60s and 70s, 70s and 80s there. You get worse on this discrimination, these details in your memory as you age. Now, by the time you've hit MCI, you're doing really pretty poorly on this. Now, it may be the case that these folks truly have flattened out. It can also be the case that by the time you're in your 80s and you're able to come into my lab for 3 whole MRI scanning sessions and many, many hours of neuropsychological testing, you're doing really well. So we don't know truly on that. We do know, though, that that very simple kind of memory doesn't change a whole heck of a lot with age. So this one metric inside this task can pick up on hippocampal function, and we can see that the hippocampal functioning does decline with age. All right, so why does it decline, though, with age? What's going on here? Well, in studies of rodents, one of the things that they've been able to see is that the actual connectivity inside of the hippocampus is changing with age, outside of anything like Alzheimer's disease. This is a sort of a diagram of how the hippocampus is wired up, and these red lines are things that are changing in rodents with age, where we can completely rule out that this is full-blown Alzheimer's disease. So we can see that these things change with age in animal models, and using neuroimaging, we've been able to do the same kind of thing in us. We can do things like use diffusion-weighted imaging, which actually lets us look at the underlying microstructure or the integrity of that microstructure, and also look at the connectivity of the brain. We can make pretty pictures like this too of really the connection diagram in the brain, but we can see how these connections change. For example, we can hone in on some little tiny connection here, this connection leading into the hippocampus. And we can see that, yeah, it actually declines here with age. The green line is what the young perforant path looks like. The blue line is what an older perforant path looks like on average. And we can make a whole bunch of folks here. So this is early work first done in collaboration with Mike Yassa when he was in my lab, and then with Alana Bennett when she was in my lab, showing how then these connections in and out of the hippocampus are declining with age. And in fact, how strong these connections are, really regardless of your age, can actually predict how well you can do my memory task here for the details. So that's pretty cool. And we can see, we can zoom in now. This is some very, very recent work. This just came out this year on looking within the gray matter as the neurons are talking to each other. They're little microscopic connections as they're talking to each other, or at least our way of being able to get that in neuroimaging. We can see that this changes here with age in the hippocampus as a whole, and even in specific subregions of the hippocampus. Research in my lab has been able to pick this kind of thing out here. And we can then see that this, again, this sort of microstructure, how well these neurons are talking to each other in terms of their for physical connectivity, that seems related to your memory performance. And the idea then is that as we're aging, it's leading to changes here in the underlying microcircuitry, which is leading to changes in your memory ability. It's not that age directly leads to a change in your memory ability. It's that age is altering your brain, and these specific brain changes are what's leading to your changes in memory. And we've got some evidence right now to really try to tighten up that story. And that's all really pretty cool. So the take-home message, we can say that, yeah, our memory does get worse with age. And in particular, we keep the gist and we lose the details. And at least some of this seems to really be tied to age-related changes in hippocampal circuitry. Now, for a researcher like me, this is really exciting because this is giving us understanding as to how the brain is changing, how typical aging is leading to different changes than Alzheimer's disease. Can we tell one from the other? And this is all great stuff. But if you notice, my beard is getting kind of whiter these days and everything. And so we start thinking a lot more about things like, can we do anything about this? So, well, let's turn back to the rodents here for a minute. And in rodents, there's a phenomenon called environmental enrichment. And in environmental enrichment, just letting a rodent lead an enriched life has a positive effect on its brain and its hippocampus in particular. So in a standard environment, you may have 4 mice that live in a little box there. Now they're safe, there are no predators overall. It's a reasonable enough life. They have food, they have water, they have each other and all that kind of thing. It's not all that rich an experience. You know, we sort of call this the COVID quarantine condition, perhaps. You know, whereas if you give them something as a bigger environment with more to explore, more things to do, more things to interact with, these tunnels to go in, these objects to play on, a running wheel even. You just give them this world to live in, and it does all sorts of great things. So for one thing, there are actually only 2 spots in your brain as an adult where you are getting new neurons born in. One of those spots is inside the hippocampus, this dentate gyrus, or GG, that I've shown on a couple of the slides there. In fact, actually, those are the green neurons here. This is some data out of Rusty Gage's lab. And this data down here is by Freund, showing that mouse by mouse, the individual mice who decide to go and explore their world and interact with their world more, those get more new neurons built, into their hippocampus, born into their hippocampus and incorporated into the memory circuitry there. So exploring the world seems to maybe actually drive new neurons being created inside your hippocampus. A lot of other things come along with it as well. Neurotrophic growth factors, a lot of things then that can be leading to this circuitry actually working better. That's an interesting idea. Can we take this same kind of environmental enrichment, though, and not have it be in a mouse? Can we do it in us? Because I don't just want to have really, really smart mice as we age. I'd like to have us be that way, too. So how can we do that? Well, could we translate it directly and take people and put them into huge environments like this here where they get to climb around and explore and all that kind of thing? I mean, I guess we could. I'm going to have to ask Frank if he'll build something like that for me. But also then there's liability issues. If they fall off one of these things, that probably isn't going to work all that well, and again, maybe you're in your 80s, it's going to be a little bit more difficult to, okay, so obviously I'm being facetious and joking here, but these are all ways in which you could be living, whether it's a complex spatial world like this. Here's a play center in Baltimore. Here's actually an ancient city that they made underground like this, which is a pretty complex layout to try to learn, orienteering or geocaching or something like that. Maybe, though, there's another way we could do this. Now, I wish I could take credit for this idea. Brilliant idea. It was Dane Clemenson's idea. He was a postdoc in my lab at the time. And what he said is, could we actually use video games instead? Large 3D immersive video games, could we use them as a way to give people a rich, complex experience and something to learn, some new information to feed their hippocampus? Could we do that? Now, when I first heard the idea, I thought there was absolutely no way this was possibly going to work. But he was shifting from testing rodents and everything to testing humans. So I said, okay, fine, Dane, go ahead. We can actually go and try to run this. But honestly, I was saying to myself that, come on, really? Playing video games is actually going to improve your memory? No. Yeah. Okay, so this is the very first data that we got on it. And what he did is he said, okay, let's go and let's find a whole bunch of people here at UCI, and let's go and give them that memory test that's really sensitive to hippocampal function. And then he split them based on whether they didn't play video games or whether they did play video games. And the students who played video games did better on my memory test than the students who didn't. Okay, that's something, but it also could, there are a lot of things it could still be. So we wanted to see if we could actually move it ourselves. So we took about 75 people, and these were all folks who didn't have any real gaming experience to begin with, undergraduates again. And we said, okay, look, we're going to divide them into 3 groups. One group, we're going to test you, then we're going to do nothing for 2 weeks, and we're going to test you again. And then we're going to wait 2 more weeks, and we're going to test you again. All right, that doesn't sound all that exciting a group. That's our control group. And in our 2 active groups, we said, let's have one group of people here play Super Mario 3D World. Now, it's a very simple kind of game in that it's designed so that total novices to gaming can do it. It's meant for even for little kids all the way through teenagers. And it's enjoyable, but it has a map that you are constantly going around and learning, automatically learning where things are. Without even trying, you're automatically doing this. So we had people do that, or we had people play Angry Birds. It's a very simple game. It's an addictive game. It's an enjoyable game. You pull this little bird back on a sort of slingshot, and you shoot him into, and you try to knock over a bunch of pigs. Don't ask me to explain why or whatever, but honestly, it is fun and enjoyable. So what did this actually do? Well, if you were launching birds into pigs, they're in Angry Birds, or you were in the no contact control, it did absolutely nothing. That's the blue and the green line there. Totally flat. Test you, test you, test you, No improvement. But if you played Super Mario for half hour a day for 2 weeks, their memory got better. Their memory completely independent of this actual task, of the actual game. It got better. And when we tested them 2 weeks later, it was still showing signs it was elevated. So playing this game made their memory better. In fact, actually, the more they explored in the game, the more they improved on it. All right, that's pretty cool, but we want to be able to replicate this, and we also want to be able to get it out just of college undergraduates. Their memory is already pretty darn good. Why should we go and improve them? I mean, come on. So, well, we said, all right, let's go and try this now in older adults, folks in their 70s and 80s. Let's go try them. So we had same basic setup here. Had folks this time, instead of coming on into the to the lab and everything and do it, we went to their house, set up a big flat screen TV and a Wii U in which they could play Super Mario 3D World, Angry Birds, or they could play solitaire actually on their own computer there. We installed a new solitaire game. So that's another control condition. We call this a little bit more active control. So if we do that, we also, by the way, extended this here. So they had actually 4 weeks worth of testing, and we tested them before. Let them play for 2 weeks, tested them, let them play for 2 more weeks, tested them, and wait a month, and test them again. Here's what happened. I'm showing you right now just the solitaire and the Super Mario group, hiding the Angry Birds here for just a minute. Well, in the solitaire group, nothing happened. Okay, didn't improve in this case here, didn't improve their memory. So that's not to say that no solitaire could. There are a lot of things and everything is, but in this case here, it didn't improve their memory. In the Super Mario group, though, it did. We see then that they start off about the same spot as the controls, if anything numerically a little bit worse, but then by 2 weeks, they're elevated. There's a reliable increase at that point. By 4 weeks, they're elevated even more, and even out at 8 weeks, when they haven't been playing for a month, their memory is still better as a result of having done this. Okay. Now, I told you I left out the Angry Birds group. What happened there? Before I show you the data, let's think about this here for a second. You're 75. You've never done anything like this before. You have a couple of researchers show up to your house with a big flat screen TV and a gaming console and a controller, and you're learning how to play video games for the first time ever. That's an enriching experience in and of itself. Now, the game itself isn't going to have as much as Super Mario 3D World is going to have, but the experience of learning how to do that, you are learning something new, aren't you? Yeah, you are. So maybe there's going to be an effect that would be somewhere in the middle. And there was. So this is a dose-dependent effect. The more novel stuff that you are exposed to, the more your memory improved. Well, that's pretty cool. We've now done this several times. In fact, we've done 5 studies on this, about 300 participants. So not a small number of people. And each time this has worked. What I'm showing you here is now just taking those line graphs where you get to sort of see the increase over time and collapsing them into start, end, not the washout bit, but start, end, how much of a difference, how much of an improvement did we really see? And I'm color coding these then in that dose-dependent effect. So that gray is always going to be the lowest. That's our control condition. Blue is going to be some intermediate amount of novelty we're giving you, and red is the most. So remember, in the young folks, it was that Super Mario 3D World that really worked, and the Angry Birds, which to the young person was like, yeah, I mean, come on, I'm not really a gamer, but I've done stuff like that before. Okay, so that's the young group. There's the older group there. Angry Birds, again, having some effect in between here. So another one here, we asked, what is it about the actual experience here? Can we really control the amount of novelty that you have? And we used the game Minecraft in young adults as a way to actually do this. And we got to control the entire experience in the world in terms of how much spatial exploration were they doing? Were they just doing whatever they felt like, or were we teaching them to be able to learn how to build new complex structures? So did they even do both of those things? And we see that there is a dose-dependent effect. You can do this kind of thing in middle-aged group. This is actually an ongoing study right now, but we're starting to see that, yeah, we can replicate this kind of thing in a middle-aged group as well. This doesn't have to be video games. We took a group of older adults and we said, all right, let's now go and do this in the real world. We made an app for their phone in which we would send them out to a park, and we had specific locations in that park, and the little app on the phone would say, go find this thing. It was a little corner of some bench maybe or something like that. Geez, I don't know where that is. Well, the phone would start saying, you're getting warmer, you're getting warmer, you're getting colder, you're getting warmer. Oh, there it is, ka-chink. Now go find another thing, and another one, and another one, and another one. So we had a big set of them, and every day they would do a chunk of them, a random chunk of them. They'd go back the next day, and the next day. In a week, they'd spend in one park, then we shoot them to another park, and they learn a whole bunch of new locations. So, okay, it's taking it out of the virtual world into the real world, and you know what? That worked as well. You give the hippocampus something to learn, you feed it information, and it gets better. It gets better at learning. You enrich your world, you give yourself something to learn, and your hippocampus gets better. That's a pretty cool message. So games are great. It's a really, really easy way to give you this kind of rich experience. There are multi-million-dollar budgets behind these games with incredible programmers and graphic designers and psychologists who are trying to make an incredible experience for you that you will pay to go and do. And that's pretty cool. And they're really rich and complex and neat. So you can do that. Put on a VR headset even and do that. We're doing some of that stuff. And that's a really, really easy way to do it. Mobility, okay, you have mobility issues, you can still have a screen in front of you and a controller in your hands. The games can be set up if they can have it so that a 4-year-old can do it. You can do it. I've had 90-year-olds doing this kind of thing. Yeah, all right. But it's not just that. We need to get lots of new information into you. So book clubs. Okay, I don't have scientific data on something like that, but going also to talks and something like this, where you are getting exposed to new information, doing outreach activities. And of course, all of these are, one day we'll get to do those again. But all of this kind of thing, or getting out and exploring your world, going for walks in new areas in particular, it's that novelty that we really think is what's actually driving this. All right, so take-home message here, part 2. Exploring these large immersive video games worlds gives us some kind of proxy, some stand-in for environmental enrichment in humans. Like rodents, our memory performance actually improves with this enrichment, and spatial exploration is a really, really easy way to do this. It doesn't have to be spatial, but it's a really easy way to do it. Your hippocampus loves soaking up that information. I mean, look, you've gone on a drive in some new area or whatever, and you're seeing, ooh, look at that. Ooh, there's this. Ooh, that. And later on, you can remember, at least if you go back there again, you're like, oh yeah, I was here before. Oh, that's right. This was the spot where we stopped for lunch. And all right, this is your hippocampus that's automatically storing this information here. So the overall grand take home is feed yourself new information, new things to learn, new things to do. All right, I want to make sure to actually thank the people who've done all of the work. I get to be the one who gives the talk on this kind of thing, but all of this stuff always takes a huge team. My long-term colleague, Shauna Stark, who was in the lab for a good dozen years as my partner in crime, as it were there. She was a part of all of the projects that you've seen. You saw both Dane Clemenson and Brandon Kolarek. They were postdocs in the lab at the time. You also saw the imaging work of Hamzi. And all of this, though, at the bottom, if you notice, are a whole bunch of undergraduate researchers, not the ones who were taking the tests and experiments, but the ones helping us collect all of this data over the years. Work has been funded by the National Institute on Aging and the Dana Foundation, and also UCI's Biological Sciences and the UCI Mind. A lot of the stuff that you're seeing here now, we're doing in collaboration with the ADRC and the UCI Mind. So a number of these things, if you're helping out and actually part of the cohort here, you're going to be seeing a number of these things really coming into play. If you want to actually see a great video of the effect of some of this stuff, hear this Brain on Tech on YouTube. The show Mindfield did a whole half-hour or so special on it. It was a really, really fantastic program. And with that, I'll open it up for questions. Thank you.